All right, you guys eat well? You're well fed? I hope nobody's still hungry. Okay, we are going to start with building your air rockets, but there's a couple things we have to go over first. All right? Now, I know you guys already think I'm awesome, right? Okay. Well, let's add to that awesomeness. I actually am a rocket scientist. I have a degree in rocket science, and I'm also a pilot. Now, I'm not just telling you this so that I can brag. There's a reason about this. When I went to learn how to fly an airplane, I was told that if I'm going to fly an airplane all by myself, and I wasn't that much older than you guys, the only way that I was going to be able to fly that airplane was if I knew everything there was to know about that airplane. So I had to know everything. Why it would fly, why it wouldn't fly, when it could fly, how high it could go, how different parts of the airplane worked. I had to know everything. So before I let you guys become rocket scientists yourself, and let you guys build rockets and launch them, you need to know everything there is to know about these rockets. So we're going to send you to college for the next 4 years. Hopefully come back, let me know when you're good, okay? All right. What we're going to talk about first is Sir Isaac Newton. Who's heard of him? Okay, that's him right there. All right. Now, he lived in the 1700 area a long time ago. And he's a pretty cool guy because he actually figured out a lot of important stuff. He came up with 3 laws of motion. I'm sure you've heard of them, right? All right, well, we're going to go over those laws because those laws are what is going to govern our rockets. You can go ahead. All right, first law of inertia. Okay? Object continues in a state of rest or uniform motion in a straight line unless acted on by an unbalanced force. We're going to simplify this a bit. All right? An object at rest will stay at rest unless acted on by an outside force. Or an object in motion will stay in motion unless acted on by an outside force. All right, here's a good example. It's Saturday morning. There's a couch. You are sitting on that couch, right? Because there's cartoons. Actually, it's a SpongeBob marathon, right? Or, I don't know what shows are fun these days. All right, so you've got a SpongeBob marathon. You are sitting on the couch. You are not going to leave that couch until Mom comes over and says, you're supposed to clean your room. I'm not going to let you watch any more SpongeBob until you clean your room. And then what do you do? No, you better get up and go clean your room. So, an object at rest, you, remains at rest. You're going to stay on that couch. There's a SpongeBob marathon. Until acted on by an outside force, which is Mom coming and telling you that you have to move. Or if you're a rocket, you're going to stay on the launch pad until we light you up and you go up into space. Okay? So that is the law of inertia. All right, next. Unbalanced force. I did mention unbalanced force in that slide. What is an unbalanced force? No? Who's brave? Come on. A wall. No, not so much. Unbalanced force. What do we have for unbalanced force? We're going to talk about a balanced force. Go ahead. All right, that's a balanced force. We've got 2 football players. They both weigh about the same amount. They're pushing against each other. Are they going to move? No. Yes. Raise your hand if they're going to move. Raise your hand if they're not going to move. We are divided. Okay, they weigh the same amount. They're pushing against each other. And they shouldn't move. All right? Unless one of them is really, really strong. We're going to assume that they are not going to move. But we're going to make this an unbalanced force. We're going to add another player to the other side. Now there's more mass, more force. There's more force on one side, and they're going to move. All right? Go ahead, next one. All right, another issue with force. We've got a elephant and a mouse on roller skates. Don't ask me why. But if we were to push both the mouse and the elephant with the same force, which one's going to go further? Raise your hand if it's the elephant. Oh, there's always a few rebellious ones. Raise your hand if it's the mouse. That's my thought. All right, let's see what happens. All right, so our mouse goes further. Why does the mouse go further? Listening? Why does the mouse go further?
The elephant has a greater mass than the mouse.
Mass. The elephant has a greater mass. Again, what happened with those football players? They had two football players on one side. They created greater mass, different force. So more mass, more force. Got to keep this in mind. They're all going to come together in the end. All right, we're going to skip the second law for a second. We're going to hop over to the third law. And that is the law of action-reaction. For every action, there's equal and opposite reaction. And right now, I need a volunteer. Where's A?
That's me.
No, that's A. Push me. That was weak. That was weak. Push me again. All right, thank you. That's all I need from you, A. You're gonna take a seat. All right, so the only time you're allowed to push your teachers around. All right, we have the action-reaction going on here. What was the action? What was the reaction? All right, the action was he pushed me. The reaction was I moved. All right, where's B? B. I want B. Come over here. Turn the wall. Push. Harder. Put both hands on the wall. That's not hard enough. More. You're volunteering. This is me telling you what to do. Push. All right, you can stop. You can go ahead and take a seat. Wait, we have a little more action-reaction going on. What was the action? Pushing against the wall. What's the reaction? No, what's the reaction? No, it's not nothing. What happened? Okay. B, what's your name again? That's not Jason, Josh, Jackson? Andrew, that's right. Okay, Andrew, are you a member of the X-Men? Oh, I picked the wrong person. then your power is obviously not floating through walls. All right? I'm the Jedi. Okay, so here we have Andrew pushing against the wall, and since he's not one of those X-Men that floats through the walls, the wall did something back. The wall pushed back. All right? Now, we're talking about balanced force and unbalanced force. Was there a balanced force when A. Jason. When Jason pushed me, was it a balanced force or unbalanced force? I moved, unbalanced. Was it balanced or unbalanced when Andrew pushed the wall? Balanced, all right. The wall is pushing back with the same amount of force that he was pushing on the wall. Okay, so we're going to go to the next one. This has to do with more action and reaction. Who's ever seen a cannon fire before? TV or real life? Okay. All right. Because like all of us, we have cannons in the backyard. All right. When you launch a cannonball, what does the cannon do? After you've launched the cannonball, what does the cannon do? Shakes. Not so much. Yep. Recoil. That's the technical term. All right. So the cannon launches the cannonball, and the cannon goes back a little bit, right? All right. So we launch the cannonball. Cannonball goes really far. Cannon doesn't go back that much. Little movement. Okay, so we have a lightweight cannonball and a really heavy cannon. So which one has a greater mass? Cannon. Okay, so cannon has a small acceleration. Cannonball has a big acceleration. Remember that mouse and the elephant, right? Larger mass, smaller distance. Say that again. This brings us to that second law. I've been mentioning mass a lot. I've been mentioning force a lot. Second law states that force is equal to the mass times the acceleration. Okay? There, if you need to look at it. All right? So we've got a big mass, small acceleration. Small mass, big acceleration. Shows up again here. Go ahead. Oh, that's an awful slide. Can you dim the lights a little bit so I can see that? Yeah, there's a rocket up there too. All right, we've got a cannonball and the cannon again. On the bottom, cannon's got a really big mass. Small acceleration. It doesn't go very far backwards. Has to be equal. Remember, for every action there is an equal and opposite reaction. Okay? He pushed me, I moved. So, the cannon moves a little bit because it's got a big mass, but the cannonball doesn't weigh as much, so it goes a lot further. They have to be equal. Alright? Well, here's how we're going to relate this to a rocket. When a cannon launches the cannonball, that is an instantaneous force. Happens once, right? One cannonball, and you move. Okay? Well, what happens if I launch another cannonball? What's going to happen to the cannon? It's going to move back again. All right, let's say I launch another cannonball. What's going to happen now? What am I doing? In what direction? In that way, right? So the more cannonballs I launch, the further I move. Well, a rocket is continuous. So a rocket is as if you have a cannonball constantly launching cannons. Let's reverse that. You have a cannon constantly launching cannonballs. All right? That's going to start moving in one particular direction. That's what the rocket does. So all that fire, that gas, that burning that's coming out of the bottom of the rocket is like millions of cannonballs going really fast out of the bottom of the rocket, and that's going to make the rocket launch into space. You can go ahead again. All right. The rockets that you are going to build have to have a couple key parts, because your rockets are going to be called air rockets. Now, your rockets are not going to be like our huge rockets out there that have all the fire and glory coming out of the bottom. Sorry, we can't light anything on fire tonight for you guys. And we're all disappointed. All right. They're going to be air rockets. We're going to have an instantaneous force, similar to the cannon. But it's going to be your action and reaction. We're going to blast air inside your rocket. That's going to be the action. And what's the reaction going to be? It's going to launch. Because that air is going to push against the inside of your rocket. And what is the inside of your rocket going to do to the air? It's pushing against the wall. What will the wall do? Wall pushed back. But it's still an unbalanced force. The force of the air inside your rocket is going to be greater than the force outside of your rocket. And that's going to make your rocket go up in the air. All right? Go ahead again. All right. Your rocket's going to have fins. Now what you're seeing up there is your conventional rocket design. Now your rocket needs to be balanced. All right, balance is important. What happens if you put all your fins on one side of the rocket? What's going to happen? It's going to fly this way. All right? Now, a rocket is also a lot like a dart. Who here has played darts? Okay. Where are the feathers on the darts? On the other end of the point, right? All right, they're kind of like a wind vane. You ever seen a wind vane on top of a house? As the wind blows against the wind vane, turns the wind vane? Well, as your rocket takes off, it starts to tip this way. Those fins push it back straight. You want them at the back. It's like a tail on a kite. All right, so that's why we've got this rocket design. Fins are at the back, nose is at the top. Okay? And that's going to affect some of the important things you see up here: lift, weight, drag, and thrust. Those are the forces that act on your rocket. Hopefully we have a lot more thrust than we have weight. Otherwise it's going to drop out of the sky. So we want to make sure that we got a well-built rocket. Go ahead. All right, this is the path that your rockets are going to take, because unfortunately tonight, no, they're not going into space. I'm letting you guys down all over the place. All right, they're going to launch. They're going to have, for a while, they're going to have a lot more force behind them than gravity pulling them down, because gravity still works, right? And who's floating out of their chair? A couple of you thought. All right. So gravity is going to eventually take hold of your rocket. The force of your rocket flying up in the air is no longer going to be more powerful than gravity. It's going to start to pull it down. It's going to reach its maximum altitude. And then it's going to fall back down to Earth. It's very important that you are not standing in the recovery zone. We are not going to send you home with a rocket sticking out of your head today. All right, go ahead. All right. That's going to wrap up your little Newton's Law, so there will be a test, and then we're going to have, yes, there'll be a test. You guys are ready for a test, right? All right, well, since you're not ready, we won't give you the test, but we are going to build your rockets. Before we build your rockets, you need to make sure that those tubes are not being touched.